looking at equilibrium and Le Chatelier. So we talked about the seesaw. I raced through the two divided chambers. Also, because, again, Thursday section now gets that opportunity, presumably with the extra points in lab, I'm going to try and, again, end at 50. Okay, so let me know if it looks like I'm getting close. Our two divided chambers, reactants and products. I don't even know what you want to be talking about over there. When we start out a reaction, all we have are reactants. So theoretically, we just mix the reactants, and then we can tell the experiment, don't do anything yet. Okay, and then we can tell the experiment to go. So what we've got are these two chambers with liquid, now only in the reactant column. What happens is we can then remove that barrier. What happens to the liquid? Okay. It starts to leak out into the other chamber. So the level inside our reactant chamber goes down, and the level inside the product chamber goes up until we have an even system. That even system is now meaning that we are at equilibrium. The flow of water molecules from the reactant side to the product side is the same as the flow of water molecules from the product to the reactant. They're still constantly moving. Nothing stops at this point. It's still moving. But they're moving at equal rates, back and forth. Okay? So we're now at equilibrium. And a lot of our experiments, what we end up evaluating are the equilibrium points, because it's easier to evaluate small molecules when they've reached a balance. Okay? So Le Chatelier came along and said, well, what happens to this equilibrium if I mess with it a little bit? Okay, so one option, he says, okay, now that I'm here, I'm going to add some more reactants. So before he does that, he pauses the reaction and says, okay, magically you now can't react. And I'm going to put in more reactants. So I have a new reactant layer. What happens when I now tell the experiment it can react? Okay, it's going to have to still equal out. So the level drops here and it comes up here. Okay, so we end up with a new system where our product concentration is now a little bit higher than it started. So it's just trying to come up with some way to balance it. When we looked at the seesaw method for equilibrium, it was relatively easy to go through and say, well, what happens if your equilibrium changes? Right? And that meant that instead of having an equilibrium established dead in the middle, we could shift our equilibrium over to the sides and see how that affected the overall results, what things need to change. Okay? Because equilibrium does not mean we have equal concentrations on both sides. It just means we have a balance out between the two sides, okay, to some extent. Okay? When we're looking at the liquid system, it's not super obvious to see that we're going to have unequal concentrations. Okay? How could we change that liquid side to show that it's possible for unequal concentrations?
Add particles.
Nope. When we go, whoa, that was supposed to be an eraser. When we now go through and do the reaction, put in our reactant, when we go through and remove our barrier, our concentration is going to adjust to, again, even out. Do I have the same amount on the reactant side as I have on the product side? No. So by changing the wells, if you will, of reactants and products, we can now actually visualize what's happening with our equilibrium. So in our equilibrium or in our reactions, everything has an equilibrium. Where that equilibrium is established and what it means for the overall reaction is a separate system. Okay? So in the case for our two divided chambers, if we looked at this reaction, would we predict this to be a good reaction? Okay, you guys go in a lab and you want to run this reaction. So our equilibrium says we can go backwards. Okay? Would this be an experiment as a student? You'd be like, yeah, let's go ahead and do this. Why not? I agree. It's probably not a good idea to do this experiment. Why do you do a reaction? To get products. If we look at this reaction as drawn, how much products do we get? Very little. So I can put in a bunch of reactants and I get a very tiny amount of products out of this. So that experiment is a pretty useless experiment, okay, or one that I'm not really going to want to do or spend the time on because I'm not going to get a lot of products out of it. If we change how we, again, interpret this, we might go through and now change it to this kind of system. So when I now stick my reactants in and I tell the reaction to go, we again reach that equilibrium. Ignore volumes. I'm not good with spatial awareness. I'm actually not that bad. That's beside the point. Okay. Is this now a good reaction for us to test? We're going to get a lot more products out of this. Okay. So then the question comes in this whole balance of conservation of mass. Okay. With the water example, that doesn't work very well. What we're looking at is the number of molecules. It still doesn't balance out rightly or correctly. Okay. But it's still getting at the idea behind it. I can get more products in this system than I did in the other system. Okay. To get the proper balancing with the amount of reactants, yes. Okay. We have to level those out, and that's not appropriately there. If you're strictly going based off of the boxes as they were colored in before, yes. Okay. Either way, it still gets to the same point. We're going to get more products out of this than we would have in the previous situation. Okay. So it might be nice if we could quantify this. How could we potentially quantify this so that we know this is a good reaction? Okay, to do that, we're going to have to come up with some comparison between our reactants and our products. In that first case, I don't know, can I go backwards? In that first case, I had a relatively tiny amount of products relative to my reactants. In that second case, I had a lot more. Okay, so I want to come up with some way to explain that, hey, this reaction sucks. And this other reaction, oh, that was again the wrong button. Yeah, I get it. I'm a horrible person. And this reaction was significantly better. Okay. How could we quantify that? What are we comparing? We're just looking at products? It's the products relative to our reactants. So what we can do is once we've achieved our equilibrium, we can compare the product amount to our reactant amount, kind of like a percent yield. Okay. So what we can establish is say, well, how much products, how much reactants? And this expression becomes very, very helpful as long as I am at this equivalence point, where I've reached the end of my reaction, when I'm at equilibrium. So what we can do is now call this a new value that we call K. K is now just a constant, because every reaction will have some K value where it wants to balance out between reactants and products. It has to achieve this relationship. Okay? So we can now look at individual experiments and say, what is its K value? Okay, well, what would be an awesome K value? We don't even need to get into 100, because remember, it's a relationship between products and reactants.
39.1.
What happens at 1? Who said 1? Did you say 1 or did you say 1? You said 1. Okay, what happens at 1?
So that makes the products and reactants like equal?
At 1, at a K value of 1, products and reactants are the same. Okay. Is that a good reaction?
Yeah.
Is it a bad reaction? Okay. Why is it a good reaction? I take 4 bicycle tires and 2 bicycle frames. Okay. I do that and I achieve my equilibrium. If my equilibrium is the same, I'm going to end up with the same on both sides. So my equilibrium in that case, if I'm getting 1, is I get 1 bicycle frame and I still have 2 bicycle tires and a bicycle frame left over. So 1 bike, 2 pieces of reactants left over. Is that a particularly good reaction? Could I make that better? How do I make that better? Assemble the other bikes. Okay? So ideally, at the end of a reaction, how many reactants should we have? 0. I don't want any reactants. I want everything to be converted across into products. Okay? That is impossible. We can't do that. Okay? There is always some concentration of reactants.
So is it kind of like balancing
It is a balance of equations almost. So we're looking at that balance between those. What value would I get for the equilibrium constant, this K, if my reactant concentration is incredibly low? It's a hard question, because we could just guess, just pick a number, say, put in the calculator, 1 over 0. 0 is as small as we can get. What happens when we punch that into the calculator?
Undefined.
It freaks out. It doesn't understand how to do that. Okay, so don't pick 0. Pick a ridiculously small number. Pick 1 divided by 0.0003. What happens to K? It becomes bigger. The smaller our reactant concentration gets, the larger our product, or our equilibrium constant becomes. That is going to be our ideal situation. We want our reactions to go as much to our products as possible, which means our product concentration is massive and our reactant concentration is tiny, which means the K, our equilibrium expression then, or K value, okay, becomes a really big number. So if I run an individual reaction, or I'm trying to decide if I should do a reaction, I can try and find the K value or come up with some way to predict it. And if that number is really, really big, that's probably a number that or probably a reaction that I'll want to do. What if that K value is very, very small? What does that mean? Why is it a bad reaction? If for K to be very, very small, what happens to the products and reactants? I've got a ton of reactants and no products. What is the smallest value I can get for K? Think of a really small number. It's the smallest number that you can think of.
A mole, negative mole.
Say that last one.
Negative mole.
A negative mole. Is a negative number smaller than any positive number? Yeah, so we can think of a lot of negative, really small numbers. Can K be negative?
Sure.
Why are you saying no?
You can't destroy, create or destroy.
Not quite.
Products or negative reactants.
How do we have a negative concentration of products? We have so few products that it's opposite of existence. Okay, that doesn't really work. How can I have negative reactants? I have so few reactants that they are the opposite of existing. I can't have negative products or reactants, which means the smallest value I can get for K would be 0. Okay? And no, we don't have ghost chemicals. That doesn't work. Okay? So we're looking at and evaluating that number. Okay? And what Le Chatelier's principle was saying is that once we've achieved that equilibrium, everything wants to get back to it. So if I start changing the concentration of products, I'm no longer at equilibrium. So this equation doesn't hold true. But what the experiment will do, or what the reaction will do, is start changing those concentrations back and forth until it reobtains equilibrium. So we're looking at this constant flow, constant back and forth. So it's kind of a neat process, which is kind of what I was going to talk about on this slide. So what we've got is our reactants going towards our products. What would our K value be for that first, or that top example?
39.1.
Should be 1. Why should it be 1?
1 to 1.
Okay, we're looking at the exact same box values. In theory, that triangle's in the dead middle. We've got the exact same products and product concentrations as we do reactant concentrations. Okay. What happens to achieve equilibrium? That sounded exciting. Here. Now on the left. There's my blue box.
There's no red box.
Okay.
Smaller.
You have to predict what the red box should be.
Small.
Why does it need to be a small one?
Physics.
Physics. It's a little bit more descriptive than science, but you know, it gets us there. To balance those out, I now need a very small weight at that end. Okay, so that everything balances. What would my K value be in this case? This should now be,
Quarter.
what was that?
Quarter.
What do you mean by a quarter? I kind of agree with that.
That's like a fourth away from.
So what you're doing is doing a comparison of what we've got within those individual masses. All we're really trying to say is that we have a value that should be small. Okay? Small in comparison to the strict equilibrium that we looked at to begin with, 1, where the concentrations are the same on both sides. So in this case, we end up with a value smaller than 1. So you picked a numerical value, that's okay, but we could have just as easily said, I see you, some number less than 1. Okay. It's also going to be greater than 0. Why is it greater than 0? I can't have negative boxes on there. It doesn't work.
That's what I was going to ask, if you could write that it was greater or less than.
You can just stick with greater than or less than, yeah. What happens if we now move to the other one? And I'm going to go through and now draw, again, our blue box.
Can I switch from one big giant?
I now need a giant red box
Doesn't work to fall off the seaside.
to balance this out. What happens to the K value?
4.
Infinity, so that's again, we're getting a really big value, bigger than 1. All we need to say is it's bigger than 1. Given the choice, going into lab, which experiment do you want to run? The one that has our biggest value for our K, because that one's going to get us the most product out of it. You okay there? Okay. So what equilibrium is dealing with is looking at those relationships and then trying to draw conclusions or predictions. You've got enough water. Okay. That's what our equilibrium is balancing around with. Okay. Questions on that? It's a neat little process that we have greatly simplified. Sorry, so let's go back to this. What we were talking about is our strength of acids and bases. That was really our primary goal here. So what we're saying is that we're starting with now a new reaction where I have an acid. Why would I write HA? Let's be extra fancy. How do I know that's an acid? It has a hydrogen in front, and technically we're saying the aqueous. If I add this to water, this would react to produce, what would our product be? If HA is an acid, what would our products be? Water is not going to be an answer. Sorry. Said this is an acid. What do acids do?
Corrode.
Give H+. So if we're now going to look at HA on the product side, it can no longer have H+. So what would be drawn? If I get rid of H+, what do I have left? For some reason I was saying Cl, but you're right, it's A. Is it just A? Why A minus? We removed H plus. Okay, so to balance that out, we have to have A minus. What else would be produced? H3O plus. We've now predicted our reaction. What equilibrium says is that we do not go from purely reactants to products. Our products can also go back to our reactants. So we now have an equilibrium here. Okay. Are all acids the same level of danger? Okay, no. If you stuck your hand in sulfuric acid, that's going to be a bit more problematic than if you stuck your hand in orange juice. Both of them are acidic solutions, one much less dangerous than the other. What does that mean is happening with our reaction, and in particular, with equilibrium? I don't know. It's our acid broke down. Okay? That's what's causing the reactivity, is our acid has to be dumping that hydrogen somewhere. In this case, it's dumping it to water. So in the case of sulfuric acid, what's happening? Do I have any reactants?
It's just by itself.
Say, sulfuric acid, we said, was more or less dangerous? More dangerous. So if we're looking at sulfuric acid, what it is doing is getting rid of the hydrogen. Which side of the reaction shows the results of having lost the hydrogen? The product. So in the case of sulfuric acid, where our A, let's just call it HA, is H2SO4. I'm going to line this up in the appropriate spots. What ended up happening? We have a whole bunch of products and very little reactants. What would our K value be? Really, really, really big. In the case of our orange juice, I'm just going to say HA equals, for lack of a better descriptor, OJ. What happens? We have very small amounts of our product. And our K value is now much less than 1. So we could look up K values for our individual acids to predict something about their strength. Okay, so that's awesome. We have a way to quantify things. Right? And believe it or not, I've had a lot of students say, well, I want to quantify. Give me an equation. Give me numbers. Okay, well, this is a perfect case where we can bring you numbers, and I can almost guarantee you as soon as I tell you you need to know the numbers, you'll immediately switch your mind and say, I don't want to memorize the numbers. Every single acid has a K value. How many different acids are there?
27.
Thousands, if not millions. Do you really want to know the K value for all of those?
Sure.
Okay. Okay. That's a lot of stuff for you to have to go through and memorize. So what you need to understand is come up with some way that you can interpret this. Take it a step further. A lot of your friends probably haven't taken a chemistry class. They don't understand what's happening with these K values and what that means as far as the reactivity of the acids and bases. But if you offered them a container of orange juice versus sulfuric acid, even change it up, we can go with hydrochloric acid, and said they had to stick their hand in one of them, which one are they going to stick their hand in? They will probably unanimously stick their hand in orange juice. Because why? They're already familiar with some of these terms. You already knew coming into this class that hydrochloric acid was bad. Sulfuric acid was bad. Okay? That those were dangerous chemicals. But you didn't understand K. You didn't understand these K values, what they meant. Okay? So what does that mean? Well, ultimately what that means is that we as chemists have changed our interpretations, and instead of memorizing all these K values, we've changed our interpretation, we've simplified it to make it easier for people to say, that is a very bad acid, that one is okay. Okay?
Where does the pH scale come in?
We'll talk about that in a little bit too. Okay? So, can you name or provide a name for, say, hydrochloric acid? You know that as what?
Bad.
Yes, it's bad. What were you saying?
It's HCl.
Okay, it is HCl. What type of acid is it? It is corrosive. I know. I'm really fishing for a word, and it's going to be really hard to find. I'm hoping it comes out.
Strong.
There we go. It's a strong acid. Okay. Some people got it. That's all that matters. Okay, this is why you attend lecture, because you didn't get to watch the awesome demonstration on the video. Okay. It's a strong acid. So we've come up with these terms. Sulfuric acid, strong acid. Hydrochloric acid, strong acid. You're aware of those because those are chemicals that typically get talked about or floated out in the standard environments. Okay. So what we want to be able to do is come up with something where we can say these are strong acids, these are weak acids. How do we decide that difference? One option is to go back to the K values. Okay? So anything with a massively high K value, we would say is dangerous, or we would call it a strong acid. Anything with a K value that's not so large, we could call a weak acid. Okay? We're not getting into the good or bad quality necessarily. Okay? So when we go through and look at these, we're looking at some different definitions. So our strong acids, yes, comes back to ultimately these large K values. So if we go into our equation again, for those of you wondering, I do know how to spell reactants. Just give me, calling it Raoul was probably not the right way to spell it.
Yeah.
I wish reactants would be Raoul. Awesome.
Reactants to
Chemistry.
products. When we're looking at strong acids, we have defined them as completely ionizing in water. Okay? So what that means is as soon as they hit water, boom, they are now products. So what does that mean for your K value? Incredibly high. Right? Infinitely high when we're looking at the K values for our strong acids. So if we drew out a reaction for HCl plus water, following the standard format that we've been doing, we got our equilibrium arrow, we'd end up with H3O plus and Cl minus. A strong acid completely ionizes as soon as it hits water, which means I end up with the products, and only the products. What can I fix about this reaction so that we know only the products are formed? It's a really simple fix. What did I change?
Maybe no reaction instead of equilibrium.
It only becomes a product. We don't look at it as an equilibrium. Okay? So it completely dissociates. There is no equilibrium. If we then move to, say, a weak acid, it's kind of a curveball, but let's throw it in there anyway. HF. HF is a weak acid, so it does ionize, because it is an acid, but it also reverses. So by looking at the reaction, we can say that HCl is a strong acid and HF is a weak acid. A lot of that information we had to already know. I knew something about their K values. Okay? I also knew another piece of information. Okay? Knowing all those K values is a bit tedious. Right? In fact, I don't know the exact K values for these. But what I do know is what I was told to memorize, and probably didn't until 5 years later, the strong acids. There are certain acids that we define as being strong. So by definition, they completely ionize in water. These are the ones that we have to be incredibly careful around. You'll notice, what do we see on here? Sulfuric acid and hydrochloric acid. Okay? So we've defined those as our strong acids. Those are the ones we want to watch out for. Are there other strong acids? Yes, there's a lot of other strong acids. Do you need to worry about those strong acids for this course or 151 or 152? No. You were told to memorize 6, maybe 7. I only remember 6. Everybody changes how many you're supposed to memorize. Okay? So if you move on into other classes, they expect you to know that those acids are defined as strong. What happens when we move over to our bases?
They're super slippery.
We can look at their physical properties. They are slippery. Okay? And on our bases, the ones that we've defined as being strong are the ones that supply hydroxide. If you think back to the Arrhenius definition, the Arrhenius definition for a base was hydroxide. Okay? But it has to completely ionize. So you'll notice lithium hydroxide, calcium hydroxide, which is actually a misnomer on there. Most of the group 1A and 2A cations bound to hydroxide are classified as strong bases. Why are they classified as strong bases? Did you say duck stamp?
Sure, why not?
What type of bond do we have between lithium and hydroxide? An ionic bond. What determines its solubility?
Water.
So solubility in water, you're going to add the water part. Based on what we talked about probably Tuesday, maybe last Thursday, talked about intermolecular forces, we have an ionic bond. We almost always say the ionic bonds are soluble in water, okay, and they're weakest. Okay. So we would predict this to be soluble in water. There's another reason why we would predict this compound to be soluble in water. There are 5 types of reactions. Name the 5 types of reactions. And if I don't get the 5 types of reactions in 30 seconds, we'll turn it into a quiz.
Dipole.
That is not a reaction.
You mean like single replacement double?
Single replacement, double replacement. Neutralization. 15.
Reversing. The reverse replacement. Decomposition.
Decomposition.
And triple.
Opposite of,
Segregate.
what was that?
Segregation.
No, opposite of decomposition.
Reassemblation.
Combination.
Same thing. Same thing. So what's the reason right there?
Yeah, it was a little close. I think we were a second or two past. But, okay. Those were our 5 types of reactions. In those 5 types of reactions, you are expected to predict products for which of those 5 types?
Neutralization.
Neutralization, single and double. Which of those 2 determines if a or those 3 determine if a reaction occurs by solubility?
Double replacement.
The double replacement reaction. Why is lithium hydroxide a strong base?
Insoluble.
If it's insoluble, did it completely ionize in water? No, lithium hydroxide is soluble in water. According to our solubility rules, which I told you to memorize, where the first rule was anything bound to group 1 metals is soluble. Okay? So our strong bases tie all the way back to our double replacement reactions and predicting those solubilities. Okay? So lithium hydroxide is exceptionally soluble in water. Because it also supplies hydroxide, we now have a strong base by definition. Okay? So there on our list, we've got maybe 14 different things to memorize. We now have all the weak acids and bases that we have to go through and memorize. Oof. How do we know if we have a weak acid or base? If it's not one of the strong ones, all you have to do is memorize the strong ones. The weak acids and bases are everything else. Okay? Questions on that? Yeah. It's a good question. In this context, I don't think so. Yeah. Next part about this. What we're concerned about is ultimately safety. So what we're looking at is the concentration of each of these species. If we take the concentration of hydrochloric acid and we up the concentration, there's now lots and lots of H plus ions floating around in that. And the H plus is really what causes them to be dangerous, what causes them to be acids. So if we've got little Timmy running around and we say, hey, watch out for that 0.15 molar H plus solution, what the heck does that mean? Right, that's not particularly easy to explain. Okay? You have to go through and explain first off decimal values. Oh, that's awesome. We know how much we love decimals and fractions. Yeah. Not only that, we've got this capital M. What was capital M? Molarity, which was moles per liter. Liters may be okay, but how do you explain moles to a kid that can't even count above 10? Okay, probably even above 5. Really? You can explain to a kid?
Why would
Okay.
a kid under the age of 10 be screwing around with acid?
Chemists are weird. They expose their kids young. Okay. So it's not a question of whether or not they have access to it or not. We're trying to become safer with it. We can scale that up. I picked little Timmy being under the age of 10, but that's, if we're really going to be honest, brutally honest about this. You all walked into the lab too. How many of you knew, looking at a bottle, that, oh, that's an incredibly dangerous solution?
Usually see a little
Yeah,
bit
that's my favorite.
Yeah. So we have to come up with some easy way that we can reference this so that people can understand that's potentially okay, that's not potentially okay. We have to come up with some way to look at this.
You give it names like face melters.
Okay.
Just how you
So we could come up with an option like face melter. Okay? But if we think back to, say, even our terror alert system, it doesn't say face melter and, oh, it's okay to be outside. It's, what is it, red and green? It's not even red. It's like cinnamon and orange and peach and all those weird colors that get associated with that spectrum. We want to come up with some way that's easy to understand. Okay, well, that little kid could count up to 10 relatively well on his hands. Those are hands. We want to come up with some way that we can relate to this. And what we end up using is not looking at these weird concentrations, but we invent a new system. And what was that new system?
The new system is the pH scale. 10
We-
being the strongest.
Yeah, we'll be careful on the numbers.
I'm just kidding.
We come up with the pH scale. So the pH is designed as a way to convert these weird, bizarre numbers into something a little bit easier. That's why I said we'll avoid the numbers for the moment. Into something a little bit easier to understand. 0 to 10 didn't quite work out for us, so we go,
Sure, 114.
typically we are told 1 to 14 officially. You have negative pHs and you have numbers bigger than 14 as well. Why do we run 0 to 14? Based off of water. Those are the strongest acids and bases that you can have within a water solution. Why are we concerned about water? 70% of everything we've got is water. Okay, so water is going to be commonly found everywhere. It makes sense to base our acid scale off of water. Okay? So, this is where we get our pH of solution. So how do we do this conversion?
Does the H stand for hydrogen?
Good call. It was going to be exactly where I was going to go with this. That H stands for H+. So it's a way to relate the concentration of hydrogen ion within that solution. What does the P stand for?
Purity.
Protons are H+. Percent may not be a bad idea, but it's not percent either.
Parts.
Not even parts. Blame the mathematicians for this. Actually, I don't know who to blame for this. P means
No, you're not bringing logarithms.
the negative logarithm.
I very much
There we
dislike
go.
Okay. You're shooting the messenger. Come on. Okay.
I did count this.
So you don't need to understand logarithms. All you need to be able to do is to understand H+. We need to be able to use the concentration of H+, typically shown with brackets. Those brackets imply concentration. What units are we going to be using for concentration? That's not a unit, that's a number. Close. We're looking at solutions. So we're looking at molarity. And this is going to be moles per liter. Okay? So if I want to calculate the pH of any given solution, all I have to do is determine the concentration of H+ in said solution, and then do negative log of that. Now I have the pH. Why do I need the negative log? Why do I need the negative? Because the log brings in its own negative, unfortunately. So we need the negative portion of that, because when we go through and take the negative log of whatever that value is, we end up with a positive value that allows us to interpret a little bit cleaner and easier. Okay? So it is much easier to then reference to our kids, hey, watch out, the pH of that solution is very, very low. Well, why is the pH of the solution really, really, or why does it matter that the pH of the solution is low? Well, we can say, oh, that's acidic. Watch out for that solution because the pH is really, really high. Well, why does that matter? Because it is basic. So we now have a way, instead of looking at all of these different numbers and powers of 10 and exponents, we now have a simple scale of 0 to 14. Okay? And our kid just has to remember that 7 is our neutral system because that is halfway between being incredibly acidic and incredibly basic, where we have now neutralized those. Yeah?
How would it be touched like to the
Same thing as if you touched an acid.
Oh, really?
Yeah. So common terms that pop up with acids and bases, you've already listed off one for acids. Acids tend to be, really? Come on. Corrosive. Corrosive is the big word that usually gets associated with acids. What corrosive means is it just kind of burns, kind of eats through things. Guess what they call bases? Interestingly enough, the word they use for bases means the exact same thing as it does for acids. But we call it something else. We call it caustic. Why do we call it something different?
Because they're not the same thing.
It's a slightly different process. So that's one thing, but it's still ending in the same result. Why would I still want to keep these terms different?
Because you don't like us?
If I take a standard stock bottle of HCl, very, very dangerous, and take a standard stock bottle of hydrochloric acid or sodium hydroxide, very, very dangerous. So I got strong acid and strong base, both of them incredibly dangerous. What happens when I mix those two? I do what type of reaction? Neutralization, which produces
Lots and lots of heat.
lots and lots of heat. That heat is now incredibly dangerous. So what do we want to do? We want to minimize those two chemicals ever talking to each other. How can we minimize that?
Putting on separate shelves.
We call them different things so that we know to place them on different shelves. It's as simple as that. Now we don't have to train the workers on where to put chemicals. We just say put all the chemicals that say corrosive here. Put all the chemicals that say caustic over here. Don't mix them. Simple as that.
Well, if you get curious.
It's not that kind of class. Okay? So pH, we already said, was negative log. Okay? That's all that P means. I'm taking the negative log of the concentration of H+. Could I do the POH? Okay. What would the POH be? Any guesses? How did you calculate the pH? Negative log of H. How do you calculate the POH? The negative log of the concentration of OH. It's the exact same thing, except a low value in the POH would mean basic, not acidic. Your low value is dependent upon what you're looking at. So a pH low value is acidic. A POH, we're now monitoring the concentration of OH, which means our low value comes out as basic. You can get less than 0. Yes. Actually, before we do that, the one last thing that I'll reference here, remember those K values, equilibrium constants? Those values can also be converted into pK values. The reason why we do that is that we again convert these big exponential powers of 10 values across into something that's a little bit easier to understand because we don't have powers of 10. Those numbers usually range from about -10 up to 50. Okay? Again, because of the sizes on them. Okay? That allows us to do some interpretation. So, electrolytes. Okay, if we go back to the previous slides, our electrolyte was anything added to water completely ionizes. Well, what do we have when we have ions?
Energy, electricity.
Starting to get it all the right idea. We've got charge. Okay. What can move through charge? Electrons. So what happens if we add something to water where it brings in a bunch of charge? Now our electrons can hop from those charges through the solution. Okay. So what we end up with is now a conductive solution, and we have an electrolyte. Okay. Gatorade, full of electrolytes. What does that mean? Potassium. Careful, it's not full of potassium, it's full of potassium ion. Okay. full of sodium ion. Those are charged species, which are allowing the transfer of electric current through them. But I don't want electric current flowing through me. That's not going to be very pleasant. If we evaluate that a little bit closer, how does the impulse from the brain get to your muscles? It's electric current. Okay, we do want electric current flowing through us. We just want to control that electric current. Okay? Which is why, if you've heard of electric shock treatments, why were they doing that? Well, not just because they were sadistic. They did actually have some kind of idea behind that of trying to stimulate the electric currents already present in the body to force other reactions to occur, to try and right messed up electric currents. Sometimes it works, sometimes it doesn't. That's kind of neither here nor here. Okay? So your ion concentration allows for the passage of electric current. So our strong electrolytes, we got 3 examples up there. What can you tell me about those 3 examples? Sulfuric acid has a metal.
Consider H to be metal.
H is never classified as a metal. It can act as a metal, sort of, but it is definitely not a metal. What all 3 of those compounds have in common?
They're neutral.
What do you mean they're ionic? Not quite ionic bonds. The first one, sodium chloride and sodium hydroxide, both have ionic bonds. What's going to predict whether they dissolve in water for an ionic compound?
Yeah, that's what I'm trying to say.
They're soluble in water.
The solubility rules from our double replacements. They're all group 1 metals. Sodium, same in both those cases. Those are defined as completely soluble. Sodium chloride, according to our solubility rules, completely dissolves. Sodium hydroxide, same rule. There's another reason why sodium hydroxide is classified as a strong electrolyte. What else is it classified as? Try again. Close. Its base was right. It's a strong base. Our strong bases, by definition, completely dissociate when they hit water, which means we have a strong electrolyte. What's going for sulfuric acid? It's also a strong acid. That's why it's a strong electrolyte, because by definition, it completely ionizes. As soon as we have ions, we now have an electrolyte solution. Okay? That does not mean you should drink sulfuric acid when you're dehydrated. Okay? Bad idea.
Are salts normally always electrolytes?
Interesting question. Are salts always electrolytes? What type of bond do we have between calcium and carbonate? An ionic bond. Iron and hydroxide. Ionic bond. Silver and bromide. Ionic bond. All 3 of those compounds are salts. So not all salts are strong electrolytes. Okay. Salt is a tip-off that we should be looking at. The bond is that it's an ionic compound, which is why it's a salt. Where do we use ionic compounds? What type of reaction? Double replacements. How do we predict if we had a double replacement reaction?
Will 2 things get replaced?
What are you saying? If it's soluble, how do we know if it's soluble?
It's ionic.
That's looking at it. We can't look at it. We got it on paper. It didn't help us. How do we know it's soluble? The solubility rules. Okay? So we would look up the solubility rules for those 3 compounds, and guess what we find? They are all... Anybody got those rules memorized? They are all insoluble salts. Our insoluble salts are by definition weak electrolytes. Okay, which does seem a bit odd. If they're insoluble, do we have any ions? No, so why are they even electrolytes?
Because they themselves are
just talked about it at the beginning of the class. All reactions, yeah, all reactions have products. True. Equilibrium. Every reaction has a forward and a reverse. If these are insoluble, they go forward to being the solid. They also go backwards to being ions. Which one dominates? If they dominates backwards, they stay ions. If they're strong, if they stay ions, they would be strong electrolytes. Which one dominates? Forwards. They're insoluble. Sorry. Excuse my reach. Okay. What happens when we move to the non-electrolytes? Anybody else know, or anybody notice a big difference here? What's special about our non-electrolytes? High lava doesn't make any sense to me. What are you saying?
There's a lot of it.
Hydrogen bonds, that's possible. I can go through and mess with that theory, though. Under our weak one, we could write in HF. HF will hydrogen bond, and that'll be our weak electrolyte. Getting towards the right idea, but not quite far enough. We don't want to look at the forces. We want to look at the bonds. What's our big bond difference as we move from strong to weak to none? Our strong electrolytes were all ionic bonds. Our weak ones were ionic bonds, but insoluble. Our non-ones? Non-ionic. I can kind of go with that. Let's push that a little bit further. It's not just non-ionic. What's that? Hydrogen bonding is a force. We already got that one.
Polar covalent.
The type of bond. These are all polar covalent bonds. Okay. You can push it even further. Those are, a lot of cases, non-polar covalent bonds. So we get non-electrolytes when we increase the strength of the bonds between our individual atoms. That bond is now so strong that it doesn't break apart into the ions. So our non-electrolytes, we're looking typically at our just polar covalent bonds and our non-polar covalent bonds. That's a big freaking long word. Okay. The other thing that we can go that typically gets referred to here, these typically get referred to as molecular compounds. Okay. Don't particularly like that nomenclature system, but that's what they get called. Okay. Molecular, because when we go through to name them, we don't name them according to our ionic nomenclature rules or our acid nomenclature rules. Okay. Questions on that? Okay. If there are no questions, officially we'll move into gases. We'll see how we deal with gases. There's a whole bunch of slides on it. We'll see what happens. Properties of gases. You should, in theory, know these already. Got some big important properties. Variable shape and volume. Okay, meaning I can change the volume and the shape and it'll still maintain the gas. They expand and compress uniformly. So if I push down on a balloon, it expands and compresses evenly around it. We don't see, when we push down on a balloon, just a single point popping straight up out of it. Okay, it doesn't happen. The whole thing kind of expands and compresses around that tension. Very low densities, and they mix uniformly within the same container. One of the extra interesting properties of these is that they can and do exert a force on the container that holds them. It might be nice to come up with some way to express that force. We could just call it the gas force, but we came up with something a little bit more creative. What is that force that a gas is exerting on everything? All of you are feeling that force right now. The pressure. Pressure is our main property of our gases. Okay, so before we start moving too much into the pressure, we want to look at some of the properties of our gases, in particular ideal gases. Okay? We have to make reference to this ideal concept because the real world is way too difficult, so we change it within our modeling systems to represent ideal systems. That way it makes the mathematics easier for us to manipulate. Okay, so here are the big assumptions that go into an ideal gas. Okay, the first one, gases have, not that one, each particle has no volume. Okay, kind of an odd statement to make. Okay, would that work for us? If we were now, each of us, an individual gas particle, okay, do we obtain no volume? Okay, said another way, could any of you stand in the exact same space that I am standing in? That's going to be really, really difficult. I'm kind of going to get in the way. Okay, so our particles do not hold volume. That becomes important to us because when I move from hydrogen to polonium, if I'm looking at a gas particle, how much volume does that particle occupy? Between hydrogen and polonium, polonium being 84, taking hydrogen, our tiniest element, and polonium, one of our bigger elements. How much volume do they occupy? Hydrogen is going to occupy more volume. Why would a hydrogen atom versus a polonium atom occupy more space? Okay, opposite. That's a reasonable assumption. Why would polonium occupy more space? It's bigger. As soon as we move into the gas phase, what do we do to that statement, that natural idea of it's bigger, it occupies volume? We say that's not true. We make the assumption that our individual gas particles are so far away from each other that at no point ever in the existence of a gas is it even reasonable to assume that two atoms could be competing for the exact same space. Because of that, we can make the assumption that each particle has no volume. If we draw that all the way out to the natural extension, this is the conclusion that comes into chapter 8 for some reason. You find that 1 mole of a gas, so if I now take not just 1 atom of hydrogen and 1 atom of polonium, I take 6.022 times 10 to the 23rd atoms of hydrogen and 6.022 times 10 to the 23rd atoms of polonium. In their gas phase, they occupy the exact same volume. So when I'm now looking at a gas system, I can compare volume and moles directly. Okay. This is not another volume and mole comparison that we've already talked about. What was that other volume and mole comparison? What is our unit for volume typically? Liters. What other mole to liter comparison have we looked at? Molarity. When do we look at molarity? When we're in solution. When do we look at moles and liters? In this case, when we're in a gas. Okay. This statement only holds true when we're in the gas phase. Why do we have a similar-ish comparison when we move to solution? Well, a solution is just a mixture of two things that can move around. So if I take a solution of acid in water, it's the acid in the water, or the acid moving through the water solution. If I take a solution of HCl gas and compare it to its volume, it's now just moving through the same thing, except now that solution that it's moving through is the gas phase. Okay? So solutions, both liquids and gases, have very similar properties and very similar effects, okay, in comparisons. So when we are at STP, standard temperature and pressure, the volume of your gas for 1 mole is 22.4 liters. Let me rephrase that because that was said horribly. 1 mole of gas is 22.4 liters. Okay? That is an important conversion factor, just like every other conversion factor we've used this semester. Okay? I personally don't like it because of the conditional statement at the end. You have to be at standard temperature and pressure. What happens if you change from that? If you're no longer at standard temperature? That equation is invalid. What happens if you're no longer at standard pressure? That equation is invalid. Okay? So it only works at that condition. I think it's kind of a meaningless one to memorize. There is at least one test question based off of that conversion factor, so you do need to know it.
What is the standard temperature of pressure?
We'll talk about that in a little bit too. We'll come back to standard temperature. Yeah, that's actually the only big statement there. So let's take a quick conversion problem here. How many liters are needed to hold 2 grams of hydrogen gas at standard temperature and pressure? Same idea as we've been doing all the way through this semester. What do we want for an answer? Not quite. Thank you. Liters of. We're not just looking for liters of. What are we looking? Liters of hydrogen gas. I don't want to write out hydrogen gas, so give me a formula.
H2,
Why'd you say H2?
because it's a diatomic.
It's a diatomic element. We must remember we're looking at H2. Okay. Are needed to hold 2 grams of hydrogen gas. So ideally, grams of H2 shows up on the bottom and liters of H2 shows up on top. Do I have a conversion between grams and liters for hydrogen? That conversion factor does not exist, at least not in this question. So we can't do that directly. Can I convert the grams to anything else? We can go to moles. One of our standard go-tos is always take it to moles and see what happens. Let's take it into moles of H2. Where do I find that conversion factor? Periodic table. So what numbers do I use? 1 mole? What is the molar mass of hydrogen gas? Why is it 2.02? The formula is H2, not H. Okay. We now want to get rid of moles, so I'll put moles on the bottom, and I want liters of H2 for my answer. Do I have a conversion factor between the moles of H2 and the liters of H2? Yes, that conversion factor is 22.4 liters is 1 mole. What number shows up in front of liters? 22.4. What number shows up in front of moles? 1. Punch it into the calculator. I now have my answer. Should be about the same. Why should it be about the same? What's 2 divided by about 2? 1. 1 times 22.4. It's about 22.4. Okay? So you can do approximative techniques to figure these kind of things out. I promise I will give you this next question on Tuesday, but I want to kind of skip ahead because we still got a little bit of time left, and we're not at 50 yet. I'm watching it. Okay, so we're going to skip ahead. I promise this will be our question to start with on Tuesday. And by question to start with, I mean quiz. Probably a good idea to do that over the weekend, just saying. Atmospheric pressure. Right, so everywhere we go, there is a gas pressure. There is a pressure constantly pushing on us right now. If there was no pressure, what would happen?
It floats away.
It's a little bit worse than we'd float away. There's now nothing really holding us together, and we not implode, but explode. Okay, everything goes outwards.
Sounds fun.
Okay, so we have this external pressure, okay, and it's related back to our atmosphere. It is all sorts of stupid units come out of this, and your textbook will have you do all sorts of dumb conversions to go through and convert between every single unit. Why are there so many different units? Because there were so many different ways that people discovered and used pressure, okay, and ultimately gas pressure. The first way, or arguably one of the first ways, was this reference to mercury, the millimeters of mercury. So we took a tall glass tube, filled it with mercury, and then inverted it inside a chamber of more mercury. Okay. The liquid would stay inside the tube as long as there's enough external pressure keeping the liquid up there. But what happens if the pressure above drops? Okay. Then our liquid inside here goes up. But if it goes up there, what happens? to this liquid. It goes down. So we created a system of looking at the difference in how high the mercury was and interpreted that as our atmospheric pressure. So it's very typical to refer to it as millimeters of mercury, mainly because not inches. Why not inches? I would argue it wasn't even that it was nobody uses inches, is that it was discovered in a place that actually appreciates science, and they used a standardized unit of millimeters.
Why mercury?
Okay. Mercury has to do with this next concept of vapor pressure. Okay. All liquids have some vapor pressure. So if we took a container of water and left it out on the counter, what happens to the layer, or what happens to the water? It disappears. But you aren't boiling it. Why is it turning into the gas phase? Because it has a vapor pressure associated with it. What that vapor pressure is the ability of the liquid to immediately transition into the gas phase at any given temperature. Some liquids have very high vapor pressures. Some liquids have very low vapor pressures. Mercury happens to have an incredibly low vapor pressure, which means if I leave that container open to the atmosphere, which it needs to be so that I can figure out the atmospheric pressure, the mercury never evaporates, which means I can get a constant reading of pressure that ignores the vapor pressure of the liquid.
When did they discover mercury?
Less long ago than we would have hoped. And we are definitely done there, so we will pick up with that first example, and then we'll come back to vapor pressure.